All right, welcome ladies and gentlemen. In this video, I'm going to be talking about average atomic mass, what that is and how to calculate it. So we're going to need our notes open to where it says video number 4. A periodic table might be helpful, but you're definitely going to want a calculator. So make sure you've got a calculator for this one. So the goal for this, be able to describe and calculate average atomic mass of sets of isotopes. So first of all, just a reminder, isotope, what's an isotope? Because this is a really important vocab word for us. There are sets of atoms that are the same element, so same number of protons, but they have different masses, so they have different numbers of neutrons. And the thing about isotopes is that they occur naturally in the world. There are a few elements on the periodic table that only have one isotope, it's sort of like one version of the atom, but most of the elements on the periodic table occur in multiple versions, different isotopes, and they occur naturally. So carbon is actually a great example. The word natural is important, they're not artificial, and they also occur in set percentages. So there are 3 naturally occurring isotopes of carbon that are down here. The first one is carbon-12, which would contain 6 protons and 6 neutrons, shown here in this image. The second one is carbon-13. So this one now has 6 protons but 7 neutrons. And the last one is carbon-14, which is the one that's used for dating. Not like, hey, let's go out Friday night, but like, how old is this fossil dating? And this has 6 protons and 8 neutrons. The blue are neutrons and the red are the protons in these images. But the thing is that these isotopes occur in predictable amounts, meaning if we were to take a sample of carbon, 98.9% of the carbon atoms in that sample would be carbon-12. 1.1% of them would be carbon-13, and a fraction of a percent, an absolutely tiny amount of them would be carbon-14. These percentages are pretty fixed because we've been studying, scientists, I say we, I haven't been doing it, scientists have been studying this for a long time and have worked out these percentages based on naturally occurring samples of different isotopes. So they occur in set percentages. These percentages won't vary. It means that lots of the carbon in the world is carbon-12. That's if you find a carbon atom naturally in nature, it's most likely going to be carbon-12. Now, the way that the periodic table represents this is through something called average atomic mass, and that is the number that is written in the top left-hand corner of your periodic table. It is not mass number. We're never going to use that for mass number because mass number is for one individual atom. Average atomic mass is now what is called a weighted average, and I'm going to talk about what that means, of all the naturally occurring isotopes for a given element. It's saying, hey, let's take all the isotopes that exist for a given element, let's average their masses together. That's the mass for that element that I'm going to put on the periodic table. Now this is a weighted average. A weighted average is not a quote normal unquote average. You do not simply take the masses of all the elements, of all the isotopes, add them up and divide by the number of isotopes that you have, because that's not a fair way to average them. If we were to do that with the 3 isotopes of carbon, remember our 3 isotopes of carbon, carbon-12, carbon-13, and carbon-14. If you were to add those 3 numbers together, 12, 13, and 14, and then divide by 3, you'd get 13, right? It'd be right smack dab in the middle. And you'd say, oh, well, the average mass for carbon is 13. Oh, but it isn't. Oh, but it's not. I look at the periodic table, and the average mass, the average atomic mass, is 12.011. A weighted average takes the percentages into account. A weighted average says, hey, 98.89% of the carbon that's out there is carbon-12. It would be unfair to say that the average of these 3 isotopes is 13 when almost all the carbon that exists is carbon-12. So we're going to weight the numbers. We're going to give more weight to the number that occurs, to the mass that occurs more frequently, to the mass that has the higher percentage. And we're going to give a lot less weight to the masses that occur less frequently, which is why carbon's average atomic mass on the periodic table is so close to 12, because so much of the carbon that we find has a mass of 12, and only a little bit of it has a mass of 13 or 14. A weighted average weights towards the mass that occurs most frequently. Now your grades are actually a weighted average because I have categories of grades, right? I've got the homework grade, did you watch the videos? I've got your lab grade, did you get your labs turned in? And I have your test grade. But the three categories are not weighted equally. Tests are weighted a lot more heavily than homework and labs. So if you had a 100 on your homework and a 100 on your labs, but a 0 on your tests, your overall average is not going to be a 67, which would be what you would get if you added 100 plus 100 plus 0 and then divide by 3. Instead, it's a weighted average, so it's going to be weighted a lot more heavily towards the 0 portion, because that's the test portion, than towards the 100 portion, because the test is weighted more heavily. It's given more weight. Now, we can actually calculate this, and we are going to be actually calculating average atomic mass. And the way to calculate any weighted average, so this is not really specific to chemistry, this is just how you do a weighted average in general, is to basically take the weight, which is the percentage, and multiply it by the number, in this case the mass, and then divide by 100. Do that for each set of data, and then add them together. So the formula is here. So we would take the mass of an isotope, right, a given isotope, and multiply it by the percent of that isotope. That's kind of like the weight. When I say it's weighted, that's the weight. So you have mass times percent, and then you're dividing by 100. This is to deal with the fact that it's a percent. Like 100% would become 1, 50% would be 0.5, 25% would be 0.25, etc. And then we do the exact same thing for the other isotope. So if there's a second isotope, we take its mass of isotope 1, multiply it by the percent, mass of isotope 2, multiply by the percent of isotope 2, divide by 100. Keep doing that for the number of isotopes that you have, and then add them all together at the end. There is no dividing by 2 or dividing by 3, not at all. It is completely absent from this. You simply sum these things together when you are all set, and that's it. That's all you do. So just one quick example of how this is going to work. Iodine is 80% iodine 127, and they give us a really detailed mass, 70% iodine 126, and 3% iodine 128. Calculate the average atomic mass of iodine. So mass times percent divided by 100 plus mass times percent divided by 100. Well, first isotope, 80% is iodine 127. But notice that they gave me this really detailed mass. Let's use that. Let's not use that one. The 80% is going to, it's a nicer number. We have more information about it. So the 80% is for the 126.88. And then 17% of this mass, again, let's not use that one. Let's use more detailed one. So the 17% belongs to this second isotope. And 3% iodine 128. Again, let's use the really detailed mass. So that percent belongs to that number. Calculate the average atomic mass. So mass times percent divided by 100 plus mass times percent divided by 100. So we're going to do 80 times 126.88 divided by 100 plus 17 times 126.05 divided by 100, plus the same thing for the last isotope, the 3 times the 128.15 divided by 100. So just what does that look like? Mass times percent divided by 100 plus mass times percent divided by 100. Now, when you're doing this and you're actually doing the work out, my recommendation to you is not to try to do this math all at once on your calculator. Instead, do this math, just one parentheses, get a number, write it down. Then do this math, get a number, write it down. Do this math, get a number, write it down, and then you can just add up the numbers at the end. And when you do that for this problem, when we sum this all together, again, there's no dividing by 3 here. Not going to do it. That doesn't work that way. I've already taken care of the weighted average. First of all, I can make a prediction. Which of these masses is the average atomic mass going to be closest to? Well, it's whichever one is weighted heaviest. Iodine is 80%. That's a really large percentage of this mass. So I anticipate that the mass is probably going to be pretty close to 127. It's not going to be closest to 128 or 126. It's probably going to be right around 127. Furthermore, if you're doing this math and you get a number that is outside of the range of the masses in this problem, meaning like iodine here, it's 127, 126, and 128. If you got a number like 243, guess what? Something went very wrong. This is still fundamentally an average of these values. It's a weighted average, so it's a different type of average, but it is an average. So an average should be somewhere in between the numbers. And that's sort of a check that you can do. Did I at least do this somewhat correct? So when we do the math out for this, I got 126.78 AMU. AMU would be our unit for average atomic mass unit. That's what we're going to be using. So we'll definitely be practicing this in class, and we're going to be doing a web lab about isotopes at average atomic mass as well.